what function it is. Because we are restricting ourselves into a finite dimensional space. All right. And okay, so this is a particular type of finite dimensional space. And there are other possible choices of finite dimensional space. Let me just give you another example. The other example, let me go to the next page actually. The other example is actually our second case. So again, let's use 3 intervals. But our basis functions are different because now we allow ourselves to be piecewise linear but discontinuous. The first function is still like that, but the second is going to be different. It's going like this, but instead of going continuously down, I immediately jump to 0 and be like that. All right. And the third function is 0 over here and go up over here, directly goes to 0 over here. And let me get another function, 0 here, jumped over here and go back here like this. So can somebody tell me what dimension I'm going to have? What is the dimension of the space I will have over here? Anybody? 2 times the number of intervals, or 6 in this case. Very good. Okay. And there are infinitely many possible choices of space. For example, instead of splitting this into intervals, I can just use a bunch of polynomials, right? I can have R order 10 polynomials. That's going to be an 11-dimensional space because I have 11 coefficients. Yes? This is piecewise linear, but allowed to be discontinuous. Right, that's a different space than the previous case. Yeah, it's not a basis for this XH, but it's a basis for a different space. We can denote it as like XD of H or something like that, right? And I'm saying we can have different space. We can have a space that is a linear combination of polynomials. We can have a space that is a linear combination of sine and cosines. We can have a space that is also split into elements, but on each element it can be polynomials, or on each element it can be sine and cosines. You can think of all kinds of weird space you can construct. You can add in delta functions into this space if you want. But like basically there are so many choices, and there is a tons of research done in finite element recently. But like here, I'm going to focus on the very basics. So I'm going to stick in almost the entire discussion to the type of piecewise linear and continuous basis functions. Okay. And this has very good generalization in multiple dimensions. For example, in 2 dimensions, if you stick to triangular unstructured mesh, that's an interesting case that finite element actually is easier to do on unstructured mesh than structured mesh. Because once you have a triangular mesh, it's very easy to get unstructured mesh. You can have a piecewise linear space on this triangular mesh, right? On each triangle, you can construct a linear function. And if you stick yourself to continuous functions, then for each grid point, you can have a basis that is 1 at this point and 0 at all others. All right. In 3D, you can do the same thing with tetrahedrals. And structured mesh is actually a little bit more cumbersome because you're going to be doing this kind of a bilinear functions. That is actually not a linear function. It's linear in x, linear in y, but like in the combination, it has an x times y term. Anyway, so it's interesting it's very easy to solve problems in unstructured mesh using finite element.